My name is Cheri Bortleson, as I said, and I am actually here in Bellevue School District in Washington State. My role is a K-5 computer science implementation leader and STEM implementation leader. We, just to give you a little perspective on how we arrived in our conversation with Dr. Jeannette Wing today, we received a computer science education grant from OSPI for 2016-17. And with that grant, it's a collaborative grant with Seattle Public Schools. And with that grant, we have developed integrated lessons for teaching computational thinking in K-8. And we've also developed a computational thinking course, which we are doing with teachers this year, both in person and through an online series. So this is the one of our final conversations that we are having, and we invited Dr. Jeannette Wing to join us, and then we thought we would extend the invitation beyond the work with our Bellevue and Seattle teachers to invite people from around the country and around the world to join us on this conversation. So the resources from our grant can be found on cs4allkids.org. And really our work is around the spirit of collaboration for CS for All, really focused on equity and access for computer science in the K-12 space. A couple logistics for our time together. This will be a moderated Q&A with Jeanette. So please introduce yourself in the chat window. One note, you need to be logged in to YouTube in order to access the chat window. So I know last call we had a few people who said, oh, I can't access the chat window. You actually have to be logged into YouTube. You don't have to participate in the chat, of course, but you can just view this conversation. So either way, please introduce yourself if you are logged in and want to participate in the chat. And my colleague, Jake Duke, will be moderating the chat window. And at the end, we will take some questions from the participants and viewers on this session, questions that you have for Jeanette. So at the very end, we'll take some of the audience questions. So Jake will be moderating the chat window. So again, if you have any questions or logistical things, he can also respond. So it is my pleasure to introduce Dr. Jeannette Wing. She's currently the Corporate Vice President of Microsoft Research. And Jeanette has had a profound impact on computer science educators in K-12 and in higher education. And her work has had a direct impact on shaping the learning in our computer science classrooms with older students and young students alike. And like many of you, I've really been influenced by what she has written about computational thinking and what she said in lectures and keynote addresses. And really, the way she describes and outlines computational thinking is in such a way that we as K-12 educators can really apply that work directly to our practice with children. There's so much I could say in an introduction about her career and her influence, but as educators, Jeanette, we really want to take a moment to thank you for your contributions that have really directly impacted classrooms. I know in my schools and across this country and beyond. So we're excited to have this conversation with you today, and we're excited to learn more together and apply what we do every day with kids and computer science.
Well, thank you very much. Do you want me to just say a little bit about myself and then, you know, a few comments about computational?
Yes, if you could tell us a little bit about yourself, your current role at Microsoft, and a little bit about your background, that would be great. Right. Thank you.
So first of all, I want to thank all of you and thank you for giving me this opportunity to talk to all of you about computational thinking. And but mainly my thanks go to all of you for helping me spread the word about computational thinking. I don't think we would be here where we are 10 years or 11 years after my article without the help of the entire community around the world. And for me, the most gratifying is to see how much movement and interest there has been in the K-12 space. This is completely unanticipated. So that to me is a huge surprise, incredibly gratifying. And I could not have done this. I would not have even dreamed of doing this without the help of all of you. So let me tell you first a little bit about myself. I am a computer scientist. I got all my degrees in computer science, and I have always been in academia up until my time at Microsoft. I was first at the University of Southern California for 2 years, and then I spent my entire professional career at the Carnegie Mellon University on the faculty there, being department head of computer science twice. And in between my terms as computer science department head, I was at the National Science Foundation on leave from Carnegie Mellon to serve and work in the government at the funding agency called NSF, which funds basic research in science and engineering for the country. And it funds not just basic research, but it also funds educational programs for science and engineering for the United States. And it was in my capacity while I was at the National Science Foundation, where I was fortunate to have a national platform on which to basically voice my advocacy for the importance of computing for all science and engineering disciplines, but also for K through 20 or K through postgraduate. So I did use my national platform to help me spread computational thinking. After my stint at NSF, I returned to Carnegie Mellon, and then a couple of years later, I joined Microsoft Research. I'm currently corporate vice president. I'm in charge of all the basic research labs for MSR. MSR has locations around the world. So of course here in Redmond, but one in New England, one in New York City, one in Cambridge, England, one in Bangalore, India. And we also have a location in Beijing, China. So we like to say that the sun never sets on Microsoft Research. Now, also being at Microsoft, of course, Microsoft, the company, has great interest in promoting computing for all ages. It has participated and sponsored Code.org and other activities that promote teaching and learning of computing by K through 12 students. And obviously, we also have products and services that we cater towards the K through 12 community. But I think I'm very grateful also for the company for allowing me to continue promoting my computational thinking for all and helping support my activities, my interest. And so, you know, Microsoft really has been quite a good supporter. So that's my background. Today, I'm here to answer questions and talk more about computational thinking. Maybe if you want to start with any high-level questions, you can start with the Q&A.
Sure. So you mentioned, and as we know, you had your first writings about computational thinking and started really talking about computational thinking 11 years ago. Can you explain your bold vision that you have for computational thinking in the 21st century?
My vision is that computational thinking will be a fundamental skill for everyone, you know, to be a 21st century citizen, let alone scholar. And by fundamental, I mean as fundamental as reading, writing, and arithmetic. Now, this is a bit of a bold, ambitious vision, and it's a little far out there. It's hard enough for all of our K through 12 students to learn reading, writing, and arithmetic. But I do think that if I look to where digital technology is, where it's going, and what our students today should be learning to become part of the workforce of tomorrow, then computing is an absolute. You have, you know, I would say 10, 11 years ago, I would simply say you would benefit from knowing it. Now I would say you have to know it to be a part of today's society and certainly tomorrow's workforce and tomorrow's society. So it's a given. 11 years ago, I was putting my neck out, but now I think it's a given. And so that is what my vision was. I stated it 11 years ago, and I still believe in it. I believe in it even more because of what I see, how I see technology has grown up, and how I see all of the next generation students and people just using digital technology. I also see it from a perspective of advancing science and engineering, and beyond that, advancing all of the disciplines, whether it's humanities or arts or social science, and all professions, whether it's law or medicine, business, journalism, you name it. Every one of these disciplines and fields, every one of these professions is being touched by computing technology. And it's not just the technology, but it's the thinking behind using the technology that's going to transform and is already transforming these disciplines. Mm-hmm. And I also see it from, the corporate perspective. Now that I'm actually at Microsoft, I see that all of our enterprise customers are coming to Microsoft because they themselves, whether these companies are in manufacturing or in pharmaceutical or in finance or the government, they're coming to Microsoft because we know something about computing, we know something about software, we know something about machine learning, we know something about AI. And so these companies are going through what we call a digital transformation. And these companies are, maybe traditionally might have hired people who majored in finance or economics or biology, but now they're looking to hire people trained in computing. So it's, as I said, it's a given.
Thank you. So thinking about that, I know we, especially even starting as early as kindergarten, thinking about what, the interdisciplinary nature of computing and the influence it has on every discipline and subject now. And when we think beyond the K-12 perspective, but coming back into K-12, that idea of how those notions can drive us to think more about integrating computational thinking and computer science into core subjects areas, even starting in kindergarten. What are your recommendations or thoughts for us as we seek to integrate computational thinking into core subject areas?
This is obviously the heart of the question of how to integrate computational thinking into K through 12. And I think there are two ways to think about the question, answering the question. One is, if you think about a typical child who grows up K through 12, learning sophistication and maturity, and I don't even know the words because I'm not an education scientist or a psychologist or anything like that, but the maturity of a child growing up from K through 12 means that the level of sophistication of the concepts that the person can understand will increase over time. And so that, first of all, that means, well, if we're thinking about teaching computing or computer science to K through 12 students, it means figuring out what concept would make sense to teach a kindergarten student versus what concept would make sense to teach, a seventh grader. And what concepts do you need to teach between, kindergarten and seventh grade, so that by the time you're in seventh grade, you can actually learn the concepts that we think you can learn in seventh grade. So what I'm trying to say is that we have to take a step back before even saying how we're going to teach computer science to K through 12 to figure out in computer science what is the sequence of, or the progression of concepts that makes sense to lay out K through 12. So that's the first step. Then one has to say, well, how are we going to actually teach these concepts? And the reason I say it that way is, well, one can think about, well, when we're teaching, let's say we want to teach some kind of logical thinking to a kindergartner, maybe some Boolean thinking, or maybe some classification. What do we teach it separately from teaching, some math concepts, or do we teach it as we're teaching some mathematical concepts? And that kind of question can be asked for every single concept for every single grade, to the point where, for sure, by senior high school, we're talking about separate courses that are teaching just computer science concepts, as well as computer programming and so on. So I think all of us are still testing the waters as to how to actually incorporate computational thinking in K through 12, because first of all, we don't have a beautifully laid out progression of concepts. And second, there's still work to be done to figure out at what stage is it not just teaching these concepts by piggybacking on existing courses, but now compartmentalizing things so that we have a standalone course to teach the concepts in the concentrated way.
Mm-hmm. Great.
So I also have, examples in my own thinking about these questions are specifically germane to K through 12. So for instance, I think one of the concepts that all K through 12 students should learn at one point and eventually be able to be very adept at is the notion of what an algorithm is. And so, at what point do we actually teach algorithms as algorithms? And my example is we teach fourth graders long division. Mm-hmm. And when we teach them how to divide one number into another and get a quotient and remainder, and how to actually compute the quotient and remainder by doing this division, we're teaching them an algorithm. And in fact, the homework questions that we give them are just lots and lots of examples of executing this one algorithm. However, at least when I grew up, and I don't know what it's like in fourth grade today, my teacher never used the word algorithm. We're learning long division now, and this is how you do it. And now go home and do 100 examples, and come back tomorrow and we'll all know long division, or something like that. Mm-hmm. And that's what we do for lots of arithmetic exercises. So one question is, are we missing an opportunity in fourth grade to actually teach the concept of an algorithm? Or, and my answer is yes, we are. But some learning scientists might say, oh, no. Fourth grade is way too early to teach this abstract concept of what an algorithm is. Better to wait until maybe you're in seventh grade, because as a 12-year-old, your mathematical sophistication is a lot greater than a 9-year-old when you're in fourth grade. Now, I actually don't know the answer to that question, but that's a kind of learning science, education science that we really need to do. I think we need to do research on to figure out when does it make sense to teach what concept at what age. Mm-hmm. So that's one example.
Yeah, I appreciate your bringing to the forefront, teaching kids the actual words and the terms and the concepts that they are actually in methodology that they're actually doing. And I know I've been in a kindergarten classrooms where kids love to learn new vocabulary words, and they're so ripe for even starting at such a young age to learn the word algorithm, and then understanding that there are steps that they follow in a sequence every single day, and that's the basic underpinnings of something like an algorithm. But they love using new vocabulary and learning and discovering how it applies in different facets of their life or within the school day.
Well, the other thing is, I think that when you learn this new word that names this concept, then it empowers people, empowers the students to be thinking at that level of abstraction, to be thinking much more than I know how to divide one number into another. So that's one thing. It's an empowering, giving names to concepts is empowering. The second is specific to long division, for instance. You teach them this specific algorithm. it also pushes the creativity, I believe, of students to think, maybe there's a different way to do it. Maybe there's a different way to do long division, not just the one way that I was taught in, in this particular class. And then you can start comparing, well, which way is better? Maybe one is when you do fewer steps. Maybe it's more efficient in that way. Or maybe there are other kinds of patterns that you can recognize that will suggest, a more efficient algorithm, depending on, the numbers themselves, even or odd, and so on. So that's another reason that sometimes teaching the concept can be empowering.
Mm-hmm. Great, thank you. So along the ideas that you were talking about, to extend a question on that, what are your thoughts around assessing computational thinking and learning outcomes in K-12?
It's a very good question. It's, of course, a question that I think K-12 educators and get all the time. It's not enough to teach the material. You want to make sure that the students have learned the material. And here again is, I think, a real challenge. It's hard enough for college level professors to know how to test their students to see if their students have learned the material taught in college in computer science. There's no rhyme or reason to think that professors know how to assess their students, and they're not held to that same level of rigor that K-12 educators are. I don't have good answers to this because, again, I'm not really a K-12 expert. I think we can learn from how we teach math, how we teach physics, how we teach other science courses, because the assessments have to be analogous in some way. I think for computing, there's an additional way in which we can assess, which is we can actually use the computer. Students can write a program to show that they understand the concept. They can feed a program with specific test data to show that the program does the right thing. And also, of course, we can use the computer as a way to monitor a student's progress in learning the concept. It's like an instrument that the educators didn't have in the past, but now you can actually, and we would want to ensure that this doesn't violate any privacy concerns, but we can actually watch when students are picking up on a concept very quickly or struggling with a particular concept. And we can do this in a very personalized way, because students do learn in different ways. And this is, of course, the great hope of personalized learning and personalized tutoring. But we do have the technology to be doing that. Mm-hmm. So it may be that the way in which we assess learning outcomes will be very different because we can use technology to help.
Mm-hmm. Your comments there are related to a question we have from one of the people who is viewing this conversation. How do you think school could or should look differently because of computational thinking? And one thing you just mentioned was how we can get a window into, what students are learning and the learning progression. But how else do you think that school could or should look differently because of computational thinking?
Well, let's separate out, and I'm guilty of having just done this. Let's separate out the learning of computing and computational thinking from the use of technology in the classroom. Mm-hmm. So the last half of what I said in the last question was really about how we can use advanced technology to enhance the learning and teaching of anything in the classroom, whether it's computer science or not. So I absolutely think that the classroom of tomorrow will use technology in much more sophisticated ways. It's not just dump a bunch of laptops into children's hands and let them search the web and all that sort of stuff. That's really superficial, low-hanging fruit. It's not really using technology, especially for the teachers and the educators, in sophisticated ways. It's also not personalized to the student, which I think we can do. So let's assume that technology is going to make the classroom different in the future and make better learning, improve learning and improve teaching. And that's, of course, an aspiration. We don't have it yet. But now let's get back to, what's the future going to look like in the classroom with respect to computational thinking? And I do think that here we go back to your earlier question of, is it going to be that as we are teaching, social studies, that we bring in these computational thinking concepts naturally, or is it going to be more like, here's the computing homework question you get that's associated with social studies or history? I actually don't know. I have a feeling it will be a combination of both. I would love to see it that there's always some kind of computing question associated with any subject that you are studying, because that will show a true integration. And it may very well be like how math might be incorporated, logical reasoning might be incorporated, and writing is incorporated. We don't separate writing from social studies. Writing's just part of social studies. And then, of course, I think in the sciences, there are all these opportunities to bring computational thinking in, just because there's natural computation that occurs and calculation that occurs in the sciences. I think the interesting question is, how do we bring computational thinking into the arts and the humanities? And there, I think, let me just talk about humanities and social science and economics and those kinds of disciplines. I think there the opportunity is going to be in data. So there's lots and lots of data out there, and very interesting data now at the fingertips of educators, at the fingertips of students. And now we can do some interesting analysis on the data to ask questions and have the data answer it for us, or to explore and discover new knowledge. Because we have a lot of data, we can see patterns that we wouldn't have been able to see before because we were only looking at small amounts of data. And so that's discovering knowledge. I think we can use data to help us make decisions. And so we can figure out, we can look at a large piece of data and do some modeling to do maybe predictions or classification. And I'm thinking of some of the machine learning techniques that allow us to build these models, both for prediction and for decision making. And that is all going to be very much tied to what we teach in the social sciences and the humanities, in economics. And then finally, there's a question of, data, what I call data for good, which is, it's not just about we can do all this analysis, but we should also be asking from the social sciences, from the ethics, legal professions, are we collecting and monitoring and analyzing this data for the good of society? And so there are these questions of fair use of data, and all these types of things are ways to bring in computational thinking into the classroom. That is, it's not like you study this in your computer science class. It's really, as you're studying some other discipline, you're bringing these computational questions to play. I think the real challenge, so that's one way to think about.
Yeah, great. So I got to hear your keynote speech or your keynote address at SIGSI this year in Seattle. And one thing you talked about is and this idea of uncertainty, and question being, what is it from the outside that we need to bring in to K-12 computer science education?
This is a great question, because when I gave my 6E keynote, I spent the first few minutes thanking the 6E community for helping me in the past 10 years for spreading computational thinking, much as I just thanked you and your efforts. And then I said to the 6E community, and now, and it was in the past 10 years, trying to promote computer science to the rest of the world, to all disciplines, to all professions, and so on. And I said, now I would like to think what outside of computer science needs to be brought into computer science and the teaching of computer scientists of the future. And that's where I started my talk about embracing uncertainty. The real bottom line was to make sure that all computer scientists are trained with enough probability and statistics for the future. And this is pretty much most undergraduate computer science programs have a requirement to learn probability, maybe not statistics, but certainly to learn probability. And so that should be maintained. I think that would be for like a requirement of any computer science undergraduate degree program. I think further along, I would suggest I was suggesting to the 6E community that, if not a requirement, there should be an elective for learning machine learning and any kind of sophisticated data analytics. And again, the reason I say this is the observation that we are generating, collecting, and storing huge amounts of data. This data is about people behavior, it's about sensors in the environment, it's about everything. And it's at that point, the data is useless unless we apply these analytical techniques and create knowledge or do some action or something like that. So my point really is, if I were to look at a computer science undergraduate degree program, I would want to make sure that certain courses are taught, certain mathematical skills are learned, and that was really the point of my talk. Now, let me speak specifically about what's an example of why it's so important to learn probability and statistics. First of all, when we look at, when we, for instance, measure a system, whether it's a computing system or any engineered system, there's certain events that happen, and what we'd like to know is what the distribution of a particular event might be. And it's not enough to just look at, for instance, the mean of the numbers that we're gathering, because the distribution might look like this. A two-humped, distribution, and the mean is right in between, which actually doesn't represent any actual value of that random variable. And so you might, if you actually design your system for that point in between the two hump, then you're designing the system that's never going to satisfy any of the actual values. And so that's a simple example of why you have to actually look at the distribution, and you can't just base your system design on, say, the mean of that distribution. And there are many, many examples where over the course of decades of research in many disciplines, whether it's social science or engineering, where people are basing theories on these simplistic measures rather than looking at the actual distributions. Now, with the ability to actually gather all the data to look at the exact distribution, we can be more precise as scientists. And so that's one of the points.
Yeah. We have a question from one of our participants today as a follow-up for what you were just talking about. And she asks, do you have any ideas of what aspects of big data and machine learning could be really appropriate for elementary school?
I think that I have a couple of ideas. So for instance, I was very much inspired by this course at Brown called Computational Thinking for Humanities and Social Science. And when I was talking to and this was invented 8 or 10 years ago, it's been taught at Brown for many years. And when I was talking to the instructor who invented this course, he said one of the homework assignments was to get the students interested at all in computational thinking for the social sciences was he asked the question of the students, are Brown students elitists? And so the question is, then he asked the students, go out into the publicly available data sets and answer that question. So what does that mean? It means go to the census data that's publicly available through the census website. Look at zip code information. Find out, the income levels of these zip codes. Then look at where Brown students come from, and answer the question. Are Brown students elitist? If elitism means somehow related to income level. Another related question would be, are Brown students more liberal than conservative? And so you can start asking these questions that obviously political scientists and social scientists are interested in, but the answer is by looking at the data. And so it motivates the students, first of all, to figure out what data to look for, to go find it, and then use the data appropriately to answer the question. So I think we could do this easily in, K through 12. The kind of question I just proposed, that is something that I could imagine a junior high school social studies teacher having the students do for an in-class exercise in a group. And that's just one example.
Mm-hmm. And I think, like you were talking about asking kids those questions, the questions that are provocative and real to them and have some relation to their world. So thinking about even in early elementary school, what's interesting to them, and then talking about, well, where would you get that kind of data and information? Because I think kids are really curious about, but giving these, opportunities and that space to pose questions and let them wrestle with what kind of data would we need to find to answer that question.
Right. And then I think any biology class has the opportunity to ask all sorts of questions about nature around the students. It turns out, for instance, that mosquitoes have the beating of the mosquitoes' wings are a unique signature. And so you can imagine, gathering up lots and lots of data about different kinds of mosquitoes and classifying them based on their wing beats and asking interesting questions about, well, what mosquitoes are local to this school district? How come we don't have to worry about Zika, whereas in Houston they have to worry about Zika? What is it about, these local environments that attracts certain kinds of mosquitoes carrying certain kinds of viruses?
Mm-hmm. Mm-hmm.
And the answers are in the data.
Right. I believe it was your 60 talk that you also were discussing the differences between data and information. Am I correct on that? Am I recalling that correctly?
Yeah.
And as an elementary educator, I was really struck by that because I thought that would be really important to really make that distinction even early, at the developmentally appropriate range within elementary school. But can you talk a little bit more about that?
Yeah, so that was, actually it was through a little demo that I gave in my talk where it was a movie recommendation or rating system. So as you know, when you go to, say, Netflix and you watch a movie, then you rate it 5 stars, and maybe some other movie you rate 1 star. And over time, Netflix learns which movies you like and which movies you don't like. And it even tells you, you know, why this movie recommended for you because you watched this other movie, right? And this is very personalized. And so you can imagine this huge matrix that Netflix keeps, all sorts of people along the rows and all sorts of movies along the columns, and in each one a rating for each show that you've watched, and for each movie you've watched, a rating you've given it. And so now you can build a recommender system which would take this big matrix based on all the people who've watched all these different movies, and it would be able to predict whether you might like a particular movie or not. So that was the demo I gave, which was to say, based on just 2 or 3 ratings that I give, this recommender system could automatically predict for any other movie whether I would like it or not. Now, what's interesting is that once it determines there's a cluster of movies that it thinks you will like, then if you tell it, I like one in one of these clusters, this cluster, you're not actually giving it new information, more information, because it already has predicted you might like that movie. Mm-hmm. So that doesn't give you much information. However, if in this cluster of movies that it thinks that you will like, and you say, you pick one of them and you say, I don't like it, ooh, then you've mixed it all up. It's a little confused. You've given it some information that it now has to recompute its model for predicting whether you will like a movie or not. And so that's the difference between data. It's the same amount of data, one movie that you've decided you like versus one movie that you decided you don't like. But in the first case, you didn't really give it new information. In the second case, you gave it new information.
Mm-hmm. Thank you. I think that's helpful. Like I said, is even thinking down into elementary school examples. And I think kids now, with being, technology and computing is just part of everyone's everyday life. I think that they can understand and start to see the impacts of, even as children, their data and how that impacts different things that throughout their day.
Yeah.
So what would your advice be to us as K-12 educators who are really passionate about teaching computer science? What would your advice be to us?
Well, first of all, I love that there are passionate K-12 teachers out there who are keen to teach computer science. And when we talked earlier, I was so impressed with what you're doing, what teachers are doing, what people are, doing these things that I didn't think people would have the courage to do. So I'm just so grateful and so thankful and so appreciative, because you are, in some sense, really down in the trenches doing all the hard work, working with the students and trying to inspire them. So first of all, I do think that students are incredibly, they're smarter than you think. They're incredibly creative, very inquisitive, very curious, and I think that we can leverage that in teaching computing, because computing is really an exploratory field, and I've always said that the limits of the power of computing is only limited by one's creativity, which means it's really boundless. And so I think there are ways that, obviously, depending on the age level, one can hope to engage with the student's creativity and exploratory nature. But that's where I would definitely tap into some of the pushing of computational thinking. At the same time, computing, as you know, is all about logical thinking. And I would very much encourage and make sure that students are very rigorous in their thinking, precise in their thinking, and logical, because I do see that carrying over towards writing and reading, the kind of the critical thinking and the ability to make a logical argument, whether it's for history or English or whether it's for science. So I think computational thinking forces that kind of rigorous thinking. So there's both the creativity, but there's also the kind of the rigorous thinking. And there are so many opportunities at every grade level to incorporate that and to encourage that.
Mm-hmm. Okay, we've one question, and if anybody else has any questions, please type them in the chat. But one that actually came from a Bellevue educator was, how can I use computer science to expand my students' global awareness?
Well, I guess, let's see. This is meaning to learn about other cultures and other countries and other activities going around in the world.
Yeah, potentially, yeah. Trying to think. And I know that the school has, that where this question came from, they do have a real emphasis on an international approach to educating their students, and really that global awareness and participating in a global community is really important. So maybe, and I think some of this you talked about with computer science, especially in the social sciences and humanities, and how that can really be influential. But
one of the things, one of my views about how computational thinking can be used, you know, for instance, for the question about global awareness, is when I think about, and I'll pick on the humanities, the social sciences, is to think about how, you know, how cultures have evolved over time, how language has evolved over time, how the arts have evolved over time. And you can actually look at the, you know, trace back, you know, centuries ago, you know, some event that then has, or something that is then spread over time. So I'm thinking, I know in language, for instance, language has evolved depending on how the populations have moved and how people have migrated across the continents. That's just, you know, in some sense, that's just linguistics. Now, if we can add in all the historical events at a particular time to see why did people migrate from one region to the other? Maybe there was a war, maybe there was a famine. Start integrating the combination of what you learn in history with what you might learn about language or what you might learn about art. And so rather than compartmentalize your learning in terms of, you know, this is history and this is art and this is, you know, English class or this is literature class, why don't we start, you know, building a map of knowledge where we start seeing at any point in time, these were the current events, these were the artists and the musicians at the time and the kind of art and music they were inventing. And these were the books that people were writing and reading, and look at how they were related, or look at, and then, you know, over time, look at how the patterns evolved, reinforcing ideas, maybe diverging ideas, throw in religion and philosophy, and you have really this map of knowledge that I can imagine. Again, it is about data, but you can imagine having students, you know, visualize, you know, use computational thinking to visualize these different paths through the world and through history. So it's like a space and time map of knowledge.
Great, thank you. Yeah, great. Thank you so much. One last question, because I know we're just about out of time. What mindsets are essential for successful, and the question was students in our modern world, but actually I'm going to say like even adults, like when we think about, and I guess the question really comes back to what we really need to be emphasizing in the K-12 space so that students can be successful both if they, in computer science or just in our modern world, which, as we've made the case for, really includes computational, people who are strong at computational thinking. So what are some of the mindsets do you think that are essential?
Well, there's one mindset that I think one needs to be a successful computer scientist, and that is the problem solving, but kind of this stick to it. It's about focus and attention, and this is something I do worry about with the next generation that's kind of perhaps a little more distracted. And, I'm thinking specifically about when you're problem solving, whether it's with a computer or without a computer, there's a need to be able to really focus on solving a problem and getting to a point where you've solved it and getting to the point where you can check your solution, and knowing that you've come to some completion. And sometimes it really is a matter of the amount of time you spend on it yourself without looking for the answer somewhere. And I don't know that I'm speaking specifically about computer science here, but I know for sure in computer science, you need that ability to focus. I would imagine the same would be true for math if you're trying to prove a theorem, for instance. But I do worry that in this day and age where it's too easy to look up the answer in the web, that people aren't actually trying to figure out how to answer it for themselves first. And I think that is really key. You have to internalize the concepts, and it's not about looking up answers on the web. So that's this ability to focus and to really take the time it takes. It could take a long time, but you need to take the time it takes. And that stick-to-itness, grit, I think is another word that people use in the education world, to be a successful problem solver and thus a successful computer scientist.
Great, thank you. And that's certainly something we can take back and think about in our classrooms, both how to model that, how to reinforce that, how to, have kids, being explicit, going back to some of the things we talked about earlier in our conversation of really, bringing those up to the forefront and being explicit about that with kids, and providing those opportunities in that space in our classrooms. For students to grow and really exhibit that those kinds of skills and mindsets that are essential as they move forward. So I'd like to thank you so much for joining us, and also thank you to the participants from joining us from around the country. We are so happy you could join us. And for those of you that weren't on the call at the very beginning, the introduction, just as a side note, this was, you can find more information about our work and our collaborative work on CS4, allkids.org, where we have some resources for computational thinking and integrating into the K-8 space, as well as we will be posting our computational thinking course that we've developed for educators, so that you can use pieces of that in your own setting. Also, I'd like to at this time say thank you to Jeanette so much for joining us. What a privilege, and we just appreciate everything you've done, and certainly your time. We know you're a very busy person. Also, I'd like to extend a congratulations to you on being named the director of Columbia's Data Science Institute and professor of computer science. And we really wish you the best in your new endeavor at Columbia University starting this summer.
Right. Thank you very much.
Yes. So thank you again. And thank you, everyone. Have a great evening.
Bye-bye.
Bye-bye. Thank you.